Hi everyone, this is part one of our material on linear codes. Before we dive into the material, it's probably a good idea for us to lay out a roadmap of where we're headed. So remember that in the last chapter we discussed decision rules, including the minimum distance and maximum likelihood rules. And alongside those decision rules, we defined what are called R-error correcting codes in the binary strings of length n. So remember, an R-error correcting code is one whose minimum distance between distinct code words is bigger than or equal to 2 times r plus 1. We also discovered the maximum size of such a code, and that's known as the packing bound. However, aside from those facts about R-error correcting codes, we didn't do very much, really. For instance, we never learned any sort of systematic way for creating error-correcting codes. We never learned a really systematic way to test received strings to see if they're code words, other than just brute force comparison to every single code word. And we didn't learn how to efficiently decode received strings. That is, how to efficiently apply the minimum distance rule, again, without having to compare to every single code word. So anyway, what we're going to do in this chapter is use linear algebra to help us do some of these things. That is, to create error-correcting codes, test received strings to see if they're code words, and to decode received strings. So in the background of all that we're going to be discussing in this chapter is an arithmetic that we can place on the numbers 0 and 1 and on binary strings. So remember, up to this point, our basic alphabet of symbols has just been 0 and 1, and we haven't really been considering that as any kind of arithmetic object, but now we are going to do so. So instead of calling this B, we're now going to call it F sub 2, and it's going to consist of the symbols 0 and 1, just as before, but now we have an addition and multiplication that we'll define on this set. So for instance, 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, and 1 plus 1 is 0. So that's indicated by this operation table. Now we also have a multiplication operation that we put on F2. So 0 times anything is 0, and 1 times 1 is 1. See here, for instance, 1 times 0 is 0, and 1 times 1 is 1. Okay, that seems like a very small thing to put this arithmetic structure on this set, but it turns out to be of monumental importance. Okay, now if we put arithmetic on the set F2, we can also put an arithmetic on the set of strings of length n over F2. So in particular, we can make the strings of length n over F2 into what's called a vector space. So a vector space is an object that has both an addition and a scalar multiplication. So to add two strings together, what we do is just add component-wise. So addition of strings is addition-wise, or component-wise addition, where these additions are occurring in F2. That is according to these operations that we just talked about a moment ago. And then also we can multiply a string by a scalar c, where c again is a number, either 0 or 1. And how do we do that? Well, we multiply each component by c, where the multiplication, again, is as we described up here at the top of the screen over F2. Right, so F2n is what's called an n-dimensional vector space over the field F2. So here we're going to just practice with these vector space operations. So we're going to consider F2, 4. So these are strings of length 4 over F2. And we're going to add, first of all, these two strings. Now remember, the addition in F2, 4 is component-wise. So I first add 0 to 1 to get 1. Then 1 plus 0 to get 1. Then 1 plus 1 to get 0. And finally 0 plus 1 to get 1. So that is the result of that sum. Okay, now in item 2, we're taking what's called a linear combination of these two vectors, 1, 1, 0, 0, and 1, 0, 1, 0. So linear combination means that we're just multiplying each of them by a scalar, in this case 1 and 0, and then we're adding together the result. So what do we get here? Well, 1 times the vector 1, 1, 0, 0 is just going to be the vector 1, 1, 0, 0. And then if I multiply 0 by each of the components in the vector 1, 0, 1, 0, I just get what's called the 0 vector, consisting of all zeros. And now when I add those together, I just get 1, 1, 0, 0, which is probably something that you saw maybe immediately when we began this problem. Okay, now finally, what we're going to do is produce this set V that consists of all linear combinations of these vectors. Okay, so now what does that mean? Well, that means that we're going to be computing everything of the form A times 1, 1, 0, 0 plus B times 1, 0, 1, 0. Now that might seem like an enormous task, to do that for all A and B, but remember the A's and B's live in the set F2. So that means that A and B are both either 0 or 1. So we start with A and B equaling 0. And this is going to give us the 0 vector. And then how about 0 times the first plus 1 times the second? So that's going to be the 0 vector plus 1, 0, 1, 0. So that just gives us this. And then we have the combination that we just looked at a moment ago. And then finally, we have this one. So this is going to be just 1, 1, 0, 0 plus 1, 0, 1, 0. So component-wise, this is going to be 0, then we get a 1, and then we get a 1, and then we get a 0. Okay, so V then is this set of vectors 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, and 0, 1, 1, 0. So in the vector space F2n, if we have a non-empty set V, we call that a subspace of F2n if for any elements V and W in capital V and alpha and in the field F2, that means alpha is either 0 or 1, we have that the sum of the two vectors is again a member of V, and the scalar multiple alpha times V is again a member of V. So one thing that you should notice is that the 0 vector, just consisting of all zeros, is always a member of any subspace. And you can see that in a number of ways. For instance, let's suppose v is a non-zero vector, or v is some vector in capital V. If you multiply by the scalar 0, like if alpha here is equal to 0, then you're going to wind up with this vector here. And that vector, again, must be a member of V by this item 2. Another way to see that the 0 vector has to be in your subspace is take a vector little v and capital V and add it to itself. Instead of taking v plus w, take v plus v. When you do that, you'll wind up with the 0 vector, and that is a member of capital V. All right, so down below here we have a number of sets, and we're asked whether these sets are subspaces of F24, that is strings of length 4 over F2. Okay, so first we look at U. Now remember, elements of a subspace of F24, they must be first members of F24. And if you look at the members of U, you see these are strings of length 2, not of length 4. And so U is not even a subset of F24, and so therefore it can't be a subspace. All right, so now let's move on to W. All right, now I look at W, and one thing that I might notice is that the 0 vector fails to be in W, right? And so I would know immediately that this is not a subspace. So now let's move down to the bottom to this Z, and we'll check it, and then we'll finish with capital V. So Z, everything is looking good at the outset. This is a collection of vectors in F24. The 0 vector is in there. Now let's just see if I take any two vectors in here and add them together, do I get another vector in Z? And indeed we do, right? The 0 vector plus itself is the 0 vector. This vector of all 1s plus itself is the 0 vector, and then the sum of the 0 vector plus the vector of 1s is just the vector of 1s. Same with scalar multiplication. If you take any of these vectors and multiply by the scalar 0, you get the vector 0, 0, 0, 0, which again is in Z. And again, also, if you multiply each by 1, you'll get a vector that's again in Z. So this is a small subspace of F24. Okay, now finally we have this set V that we talked about on the previous slide. It's all the linear combinations of 1, 1, 0, 0, and 1, 0, 1, 0. So we can look at that and remember what that is, right? It's the 0 vector. It's each of these vectors. And then it's also the sum of those two vectors, 0, 1, 1, 0. And you can go and check conditions 1 and 2, right? Just try adding, adding all combinations of these vectors. You can multiply by scalars. And again, you're going to wind up back here in V. So this is also a subspace. So generally speaking, if we have a set contained within F2N that consists of all linear combinations of one or more vectors, then that set will always be a subspace. One thing that's nice about vector spaces and subspaces is that you can use a relatively small number of vectors to describe the entire space. So in the terminology of linear algebra, we call that small set of vectors a basis. So a basis for a vector space or subspace is a minimal set of vectors whose linear combinations give the entire space. Right? That's also called a minimal spanning set. And then the dimension of the vector space is the number of vectors in a basis. All right, so here we're given an exercise where we're to find a basis for each one of these subspaces of F25, that is strings of length 5 over F2. Okay, so here first we have this U, which is indeed a subspace, and the basis for this thing just consists of 1, 1, 1, 1, 1, that single string, right? Because if you take all sums and scalar multiples of that single vector, you wind up exactly with this set U. Okay, now for V, there's a number of different ways you can pick a basis for this. In fact, any two of the non-zero vectors will work, right? You couldn't, however, choose these two, right? Because if you take all linear combinations of those two vectors that I underlined, you won't get all of V. You'll get just the 0 vector and this vector 1, 0, 1, 1, 0. However, if you use 1, 0, 1, 1, 0, say, and 0, 1, 1, 0, 1, that will form a basis, right? Because every single vector in V can be expressed as a linear combination of those two vectors, and further, there's no smaller set of vectors that will suffice to do such a thing. Okay, now we're also supposed to be giving the dimension of each of these subspaces. So remember, dimension is the size of a basis. So in part A, the dimension is equal to 1. Here, the dimension in part B is equal to 2. Now, in W, we've got a longer set of vectors. There are 8 vectors here. And I think maybe now you believe that if we just used 1 or 2 of these, we would not get enough vectors to fill out W, right? If we only used 1 vector in our basis, that would fill out a set of size 2. If we used 2 vectors in our basis, that would fill out a set of size 4, and that's just too small. So we're going to need a set of size 3. And so here we need to sort of pick judiciously. For instance, let's suppose that we picked these 3 right here. Then I submit to you that those 3 that I circled are not a basis for W, because if you look at the first 2 circled vectors and you add them together, you'll get the third circled vector. And so the first 2 circled vectors together with a third circled vector will only give you a size 4. It won't a set of size 4. It won't give you everything. And so we need to be a little bit careful about how we pick these things. And in linear algebra course, you learn various ways about how to be careful. But at any rate, these 3, if you choose those 3, that will form a basis for W. So your basis is 1, 0, 0, 0, 0, 0, 1, 0, 1, 1, and 0, 0, 1, 1, 0, and the dimension of this subspace is equal to 3, because that's how many vectors are in a basis for it. Now we're ready for codes to enter the mix. So for us, a k-dimensional linear code is just a k-dimensional subspace of F2n. So you can imagine F2n as being this giant set of strings of length n. So there it is. And we want to identify in F2n what our code words are. And those code words for linear codes are going to be subspaces of F2n, like this V. Okay. Now, each of the sets, U, V, and W on the previous slide, is a linear code in F25 because each of these are subspaces of F25. And they have dimensions 1, 2, and 3 respectively. Okay, now you might be wondering a few things. First of all, in what sense are these subspaces being used to encode messages? In other words, what are the natural alphabets that are being encoded, whose code words would be these elements of these subspaces? Then the next thing is, because error correction is important, we're going to want to know how to find the minimum distance of such a code. So is there, in the setting of linear codes, sort of a relatively easy way to determine this minimum distance and thereby determine whether a linear code has error correction capability? And then finally, is there an easy way to apply the minimum distance rule? Right? Let's suppose I receive a string Z in transmission, and I want to find a code word C that is of minimum distance away. In chapter 6, all we knew how to do would be to really just to compare Z to every single code word. Is there an easier way for linear codes? So it turns out that there are positive answers to all of these questions. So here we address, or begin to address, the first question on the previous slide about how these linear codes are actually encoding messages from some natural alphabet. So we're going to let V be the linear code in strings of length 5, binary strings of length 5 with this basis. So what that means, again, is that we're going to take all linear combinations of those two vectors, and that will make a subspace, the subspace V of F25. Now we're going to define E to be this matrix, and you might notice that the columns of E are exactly the vectors that we have in our basis for V. Okay, now what I'd like you to do is to regard the strings of length 2 as being our natural alphabet. And we're going to define a code C from F, the strings of length 2 to strings of length 5, by just taking C of X equaling E times X, where this E times X is matrix multiplication over F2. All right, so we're claiming that this is a code. So the first thing in our task list is to evaluate C of X for each X in F2. So let's do that, right? So the very first X in F2 would be just the 0 string. So if I multiply by the 0 string, well, what is that? That will be 0 times 1, 0, 1, 1, 0, plus 0 times 0, 1, 1, 0, 1. And the result, of course, is the 0 vector. Okay, so we're going to go ahead and just write that down here. We're going to keep a list of these vectors. So we get the 0 vector. Okay, so now let's do this again. So we're going to take all of this, get rid of it. And we'll multiply by something else now. So let's now multiply by 0, 1. So that's another string in F2. And if we do that, we're going to get 0 times the first vector, 1, 0, 1, 1, 0, plus 1 times the second vector, 0, 1, 1, 0, 1. And of course, that's just going to give us 0, 1, 1, 0, 1. So we're going to add that to our list. And now we keep going. So we make another computation. So maybe the next string that we would have here would be 1, 0. And now we're almost done. Right? It's 1 times the first vector, 1, 0, 1, 1, 0. And then 0 times the second vector, 0, 1, 1, 0, 1, which gives us just that first vector, 1, 0, 1, 1, 0. And then finally, we multiply by the string 1, 1. So that would be 1 times the first column plus 1 times the second column. So that's just the sum of those two vectors, which would be 1, 1, 0, 1, 1. All right, so we have evaluated C of x for every single x in F22. That is every single string of length 2. And what did we wind up with? Well, we wound up with exactly the elements of our set V. All right, now remember, code functions need to be one-to-one, and I think you would agree that if you have two different strings of length 2 and you make this matrix product, you'll get two different strings of length 5 in the output. So it is one-to-one. Okay, then the question is this a linear code? And indeed it is, right? Remember, this V, the set of code words, is this subspace of F25, and so it is a linear code. And then finally, you might be wondering, well, okay, let's suppose we have a stream of zeros and ones. How could we use this coding function to encode that stream of zeros and ones? So one thing that you might do with that is, I don't know, let's suppose you have a stream of zeros and ones. What you could do is take that stream and break it into blocks of size 2. And then encode each one of those blocks using this coding function. The example we did on the previous slide suggests this theorem about linear codes. So what it says is that up to permutations of symbols, every k-dimensional linear code in F2n has this form, where C of x is just E times x, where E is this matrix, where the top bit of the matrix is just the k by k identity matrix, and the bottom is some arbitrary matrix, A, of size n minus k by k. Now, on the previous slide, let me remind you what E looked like. So E had 2 columns. right? And it looked like this. It was 1 0 1 1 0 and 0 1 1 0 1. And in that example, the k was equal to 2 and the n was equal to 5. So notice that indeed, so k is 2, so up top here we would expect to see the 2 by 2 identity matrix, which indeed we do have. It's right there. So that's I2. Remember, the identity matrix has 1s on the main diagonal and 0s everywhere else. So this is I2 right here. And then down below we have an n minus k by k matrix. So n minus k in this instance is 3. So we've got a 3 by 2 matrix below. Okay, so that was the example on the previous slide. And it generalizes to this theorem. Every single linear code has this form, where the code words are linear combinations of the columns of this matrix E. Okay, so we call X, so X is sort of a string in F2K, so it's a string of length K. And that is our message, so that's our sort of our natural alphabet object. And we call AX the set of check digits. So X is the message, and AX is the set of check digits. Right, so the columns of E, as I mentioned a little bit earlier, the columns of E form a basis for the subspace consisting of the code words in the strings of length n. Okay, here we have a three-dimensional linear code determined by this matrix E. So we have a number of things that we would like to do with this code. The first thing is we're going to identify the k by k identity matrix here and the matrix A. So notice that this is three-dimensional, and so up top in this matrix E, we expect to see the 3 by 3 identity matrix. So there it is. And then the matrix A is whatever is left down below. Okay, so we have identified I sub k and A. And then we're asked, how many code words are there? Well, remember, the code words are the set of all linear combinations of the columns of E. Now, if you don't want to think about it that way, you can think about it in terms of matrix products, right? We can think about, well, okay, how do I get a code word? Well, I would encode a string of length 3. So I would multiply E by some string x1, x2, x3. And how many of those strings are there? Well, there are 2 cubed of them. And so there should be 2 cubed code words, 1 for each of the strings in the natural alphabet F2, 3. Now, it might be sort of interesting generically to see what the code word looks like. So let's perform this matrix product. So if we perform this matrix product, what we get as a resulting vector, this is going to be x1 times the first column, x2 times the second column, plus x3 times the third column. What are we going to wind up with? Well, we're going to wind up with x1, x2, x3. So that allows us to see our original message. And then down below, we're going to wind up with x2 plus x3 and x2. So if you were to pick a specific string x1, x2, x3, it would give rise to this specific code word which is a string of length 5. And there are 2 cubed of them. All right, now we're asked to encode a stream of symbols by breaking it into blocks of size 3. So let us do that. So we break these into blocks of size 3. And let's see if we can encode that stream. All right, so let's now first look at this first string 0, 1, 1. So in that case, if you look back up here, x1 would be 0, x2 would be 1, and x3 would be 1. So x1 would be 0, x2 would be 1, x3 would be 1. So if you plug those in for x1, x2, x3, we get code word 0, 1, 1, and then 1 plus 1 is 0, and then x2 is equal to 1. Okay, so that is the encoded version of the first block. So now we move on to our second block. So there x1 is equal to 1, x3 is equal to 1, and x2 is equal to 0. So we're going to get 1, 0, 1. And then 1, 0, I believe. Right, because x2 plus x3 in this instance is going to be 1, and x2 is equal to 0. Okay, so that's the second bit of this stream. And now the last part, we have 0, 0, 1. So there x1 and x2 are both 0, x3 is equal to 1, and that's going to yield this code word 0, 0, 1, 1, 0. Okay, so this stuff here, this big long stream of stuff, that's the encoded version of this stream of zeros and ones by breaking into blocks of size 3.